All right. Again, with the laser processing regarding photovoltaics, and we are very happy to have with us Osvet. He comes from Erlangen University. We are going to have the chance to listen to another lecture from Erlangen later today, and he's going to speak about the laser processes in photovoltaics.
So thank you. Most of the experimental work that I have done personally with lasers is actually related to optical spectroscopy of defects in solid states and impurities like rare earth ions and transition metal ions in solid states. But when I started to use lasers extensively during my doctoral studies, I learned quite quickly that sometimes instead of producing spectra like this, by the way, it's the well-known narrow luminescence lines of europium 3+ and on the right 2+. Instead of producing spectra like this, I produced things like this. So what did I learn from it? You can also use lasers not only to excite luminescence, but to do some material processing. And I didn't take any photos, so I downloaded these from the LIDAR's homepage, which is specialized on laser damage of surfaces. And actually, it didn't happen very often, and it was not so dramatic, but it still clear to me that very different mechanisms are actually happening when laser interacts with a solid, depending on material properties, of course, the properties of laser pulse, wavelength, energy, and so on. And it also depends on the surface properties. Clean surface has a well-specified damage threshold. If you have dust on it or cracks, scratches, then the surface is damaged much more easily. And by the way, this is also another aspect of laser safety, which we were listening to 2 hours ago. So you also have to take care of the safety of the equipment. Now, in Erlangen at IMET, coming closer to solar cells, at IMET, photovoltaics is the core. It's not the only, but it's the core topic or area of investigations. And this area is actually very broad, involving classical inorganic materials like here on the left, thin film, organic and hybrid photovoltaics, like demonstrated here by the head of the institute, Professor Brabeck, and also several advanced concepts of producing semi-transparent solar cells, tandem cells, and different concepts. Now, this field is so broad because there is very tight cooperation between the Center of Advanced Energy of Bavaria, which is now transforming into a branch of Helmholtz, and Energy Campus Nuremberg. And at IMET, we are mostly focused on materials and small devices. And these other institutes are more involved in upscaling the production and also moving the materials to production, and also taking care of really high throughput production, and also developing a concept how to integrate the solar cells into real world up to smart grids. And in the following talk, I'm going to give a short review about how lasers are involved in the production of silicon solar cells, and then I will give you a couple of examples how lasers have been used at our groups for the structuring of organic and hybrid perovskite solar cells. So you saw already this information from National Renewable Energy Laboratory. I'll just show it to define which materials we are mostly working with, perovskite materials and organic photovoltaics, and less tandems and triple cells, which allow higher efficiencies. Now, how laser light is sorry. Thanks. Interacting with the matter, of course, it depends on the absorbance, reflection properties of the surface, its thermal conductivity, thermal capacity, melting point, and several others. And then the intensity of the light, if it is pulse duration, is extremely important, and wavelength. Now, very largely, we can divide these processes into photothermal and photochemical, which happens mainly in the excited state. Photothermal is heating up the lattice and causing sintering, melting, ablation, whatever. Now, I'm not sure whether there was a talk about laser machining. Today in the morning there should have been one. Instead, yes.
On Monday,
yeah,
the last meeting says, on Monday, Professor Stratakis spoke to you about laser,
yes.
laser patterning and laser machining and lasers.
Yeah, I was not sure what was shown. So,
but more things.
I will show.
Talk in Erlangen, because in the Erlangen, you know, the school will be devoted on this laser machining, etc.
So, how is laser light absorbed in the matter? The laser light is mainly affecting with the electronic subsystem. It can cause just electronic transitions at high or short pulse length and high intensity multiphoton transitions, which are proportional to the power of n, become important, and also absorption at free electrons, which is sometimes called inverse Bremsstrahlung, because free electrons are not able to absorb energy from the photons. They have to be in interaction with some other, let's say, some ions. Bremsstrahlung means that if you are decelerating electrons, they emit light. Inverse process is that they can absorb light. And this effect is more important at longer wavelengths in the infrared, because the efficiency of this absorption scales with the square of the wavelength. Now, there is also some difference between insulators and semiconductors, where while in insulators and semiconductors we are creating electron-hole pairs, and the recombination of them follows, and this may take nanoseconds. In metals, we have a very high density of free electrons. There is a very fast thermalization between electrons, and the thermalization may happen at a much faster time scale. Now here I prepared just one slide with a couple of thermal transport equations. So very often people use so-called two-temperature model because it is reasonably simple and gives reasonably good results. So there is a pair of coupled equations. The first one describes the temperature dependence of the electron subsystem, and the other one the phonon or lattice system. And the first term here describes the thermal diffusion. The last term is the input of energy. If you want to get a clear picture of how the temperature is distributed at the laser spot, then you have to put the time and spatial profile of the laser light into this term here. And the second term describes the interaction between electrons and phonons, or electrons and lattice, and this is the term which goes as a positive term to the lattice system. In principle, there should be a similar diffusion term here in the second equation, but there's it is a couple of orders of magnitude weaker than it is usually neglected in the second equation. And under certain equation, there's electron-phonon coupling is proportional, or the strength of this coupling is proportional to the temperature difference between the two systems. Now, at long pulse width, we can further simplify these equations because there is practically no difference between the temperatures of electrons and lattice. And if, in the case where we have a relatively large laser spot and small penetration depth, then we can reduce it also to one dimension. Now, this is one graph which I took from the book cited here. These are the editors. I like it quite because it very well illustrates the different temperatures. The first one happens at the time scale of femtoseconds. I marked the width of the excitation pulse here with this blue line. The pulse width here is 50 nanoseconds, here 5 picoseconds, and here 500 picoseconds. So there is always a difference of 100 times. And now here you see how the temperature of electron subsystem increases very rapidly, and then it starts to decrease, and the energy is very weakly transferred to the lattice. It's mainly taken away by, if it's ablation, you're just blowing the energy out of the material without heating the lattice. In the second figure, we have an intermediate situation. We have 5 picosecond pulse, and we see how the during this electronic temperature increase, there is a considerable increase of lattice temperature. And if we are talking about half a nanosecond pulse width, then we see that there is practically no difference between the electronic and lattice system. This is also an illustration of the difference between short pulse short and long pulse interaction. Here there is enough time for the lattice to be heated up. A part of the material is thrown out of this hole, and there is quite a broad so-called heat affected zone here. In the case of femtosecond laser processing, we just have practically a clean hole and very small heat affected zone. Now, coming to the review of silicon processing. Well, silicon is a very well studied material and gives good efficiency without doing much technology. But if you want to go way over 20%, you need to apply some advanced methods, and we will have a look at these one by one. So one mostly used methods is edge isolation, and this is already very broadly used in production. Then laser grooved buried contacts, also a mature technology. Then cutting silicon, also used in technology already. And some of these technologies are adopted, like emitter wrap-throughs and selective emitters. Let's have a look at all of them. So now I think half of you raised their hands that you know how photovoltaics works. Just to remind you how silicon cells are processed or produced. So it starts from P-type doped wafers, which are then subjected to surface structuring via potassium hydroxide. This is to produce the modulation of the structure to improve the coupling of light into silicon. Now, after that, there is phosphor doping step with phosphor oxychloride, which covers the surface, and after heating up, phosphor is diffusing into the silicon wafer, shown here with this red line, and it obviously surrounds the whole silicon cell, top, bottom, and also sides. And these sides are a problem for the further production, because they have to be isolated. I will show it on the next. After that, an anti-reflection coating is put on the surface. This is silicon nitride, hydrogenated silicon nitride with a thickness of maybe 70, 80 nanometers. It's a quarter wavelength. And on an electron microscope, it looks like this white layer here is the anti-reflection coating. Here once more the structure, and at the end, top electrodes are screen printed. There is a metallic paste containing silver and lead oxide. It is screen printed on the top. Then the solar cell is heated up, and this remelts the anti-reflection coating, and also and in this way there will be a contact, which is not shown probably actually in this figure, to the silicon bulk. Now, during the fabrication, so the first thing that has to be done is to cut the edges. It's shown here in the top left figure. So if you don't cut a line at these places, then the cell is short-circuited, because this red layer is very heavily doped. It's doped. Now, this is done usually with a galvanoscanner and either infrared laser. With silicon infrared, you don't need very fast or short pulses here. Picosecond, nanosecond lasers work very well. It can be done with infrared lasers. It can be done also with green, and now also with ultraviolet lasers. The ultraviolet laser just gives you a smaller groove, and the loss of area is limited in this way, and you have a nice actually a scratch at the edge. And this process is very fast. What I've read is about 1 second per wafer. Now here is another image of the groove made by an ultraviolet laser. How it looks like. The typical width and depth of the groove with this kind of laser, it may be a couple of tens or maybe 20 microns. If these grooves are made by infrared lasers, they tend to be something like 50, 60, 70, or 80 micrometers. Now, the second, here is one. Another option is to cut these grooves on the or at the bottom of the solar cell. Now, concerning anti-reflection, the structuring of the surface, this potassium hydroxide works very well with single crystalline silicon, because you have a well-defined orientation, and this process is direction selective. In multicrystalline silicon, this etching does not work well. And here, one option is also is to use laser structuring of the surface of silicon. There is also a chemical option involving an acidic solution. Now, one more thing that is being done with lasers in silicon solar cell production is so-called laser grooved buried contacts. The idea is to reduce the shading area of the electrodes, which may take some 10% of the whole area. So this way, you can reduce the area, but you can also improve the serial resistance. Here, grooves are made with lasers, relatively deep grooves into the solar cell, and then this inside of this groove is strongly n-doped to improve, to further improve the contact between silicon and copper, and then copper plating is done chemically into these grooves. So the conductivity of these conductors here is actually better than a thin film of silver on top of it. And well, in this case, the back contact is also made of copper. So one small, you save the area, the active area of the solar cell. The loss of area may be 2 or 3%, and you improve the contact between silicon and copper, and the copper itself has a good conductivity. So this is the similar groove, but with a different shape, also plated with copper, and the solar cell which has been produced by a commercial company. Now, a further option to increase the efficiency of silicon solar cells is to use so-called through contacts. It's possible to remove the contacts from the top totally by making holes with laser again into the cell. Typically, wafer has tens of such holes with a diameter of tens of micrometers. And now there are two options. We'll see them here. Either these holes are filled with copper or metal. This bottom left picture actually should show the holes. I'm not sure that they are well visible. You can fill the holes with metal and bring the top contact to the back of the silicon solar cell. Or if the inside wall is heavily n-doped, then it is also conductive, and you can just place the so-called top contact here on the bottom of the silicon cell. Of course, you also have to do some further structuring here, cutting or separating this highly conductive N-type layer. One more option is laser processed contacts. So in this, in the first case, shown in the left figure, a dopant material is put. It may be sprayed on the top surface of a silicon cell, and with laser pulses, they may be. This does not have to be a femtosecond laser or long pulse laser. Enough, it has to melt this material, which brings the dopant into the silicon cell, and it remelts silicon together with this covering layer, again increasing the doping concentration locally and improving the contacts. Another way is to cut holes into silicon nitride, the anti-reflective coating, and fill them with metal. This can be done chemically. In this case, it is critical to use laser pulses which remove only the anti-reflection coating, which you remember is 70 nanometers thick, and it should not damage or melt the silicon. So this is a more critical case. And last, I think it's last case is so-called laser fire contacts, which case you can melt the aluminum. By the way, this aluminum, well, after making the N-type contact on top, you have the similar N-type layer here on the bottom. So you can put a thick layer of aluminum, heat it up, and aluminum will diffuse into the silicon. But you can improve or increase this process also by locally melting the aluminum layer, and actually it's remolten together with the silicon, and this again improves the contact in the silicon. Now, changing the topic, what's the difference between the silicon cells and organic photovoltaics? So not only organic but also hybrid. Well, it's one thing is that you have tightly bound electrons and holes due to very different dielectric constant of the materials. In silicon, you have free carriers. In organics, you have very tightly bound pairs of electrons and holes. And to separate them, you need a different structure. Also due to very different absorption coefficient of silicon, which is an indirect material, and strong absorbers like most of the organic materials are, you need very thin layers. And this creates a very different situation if you want to do some laser processing or structuring of the solar cells. Okay. So this is just a very simple structure, a bulk heterojunction formed of two materials, acceptor and donor material. Bulk heterojunction means that you have a very tight connection between the donor acceptor area where the excitons are actually separated, but the charges are separated. So this is a nanometer scale, tens of nanometers maybe. You usually need some electrodes and electron and hole transport layers. Now, very typical materials for donors are P3HT and PCBM, which that's nothing new, but this is a very good test system if you are developing new cell architecture or production methods, or just trying to optimize laser structuring. So the involved energy levels shortly, it's not only about occupied and unoccupied levels, and the difference which should determine the open circuit voltage. Also several other energy levels involved, like triplet states, and at the interface of donor acceptor you have also charge transfer states, and a lot of chemical engineering is being done to optimize these materials to increase the open circuit voltage. But now to develop the laser structuring, this combination of P3HT, PCBM is very good because all the chemistry and technology is very well known. Now, one problem with thin film, not only organics, but with thin film solar cells is that the serial resistance tends to be high, so they have to be structured. If you just make a sheet with several square meters, then you will have huge losses. So they are usually structured into this into ribbons like this. And these ribbons have to be connected serially. This will increase the output voltage and reduce the current. And there is a better picture on one of the next slides of how this structure works. Here it's a three-dimensional image of these ribbons, and the equivalent electrical scheme, and the current path is indicated here. How can this be done? If you are, well, the main advantage, or one of the main advantages of organic photovoltaics is that it is solution processable. So, if it is solution processable, it is printable, and it can be applied also to roll-to-roll production. And this way you can print the cells in these ribbons and do the structuring. But the losses, the area losses, tend to be very large in this case. The geometrical fill factor is not very high. So what can be done? You can take a laser and do the structuring from the very beginning. The gray ribbon here shows the substrate, whatever it is. Then comes, say, the first electrode, the transparent electrode, because the light comes from the bottom here. You make grooves here with the laser. Then you can put the active layer, here shown consisting of 2 parts like donor and acceptor, on top of it. Then you make a new groove, which is called the P2. The first one was P1. You make a new cut here, or groove, and then you apply the top contact. And now you have to isolate these single cells by making another cut, which is called P3 in this technology, with laser. You can do it from the top to the bottom, and so the current path will be from here to here, up there, again here, and so on. Now, for this, this technology is also used not only in organic photovoltaics, but in thin film silicon, in cadmium telluride 6, and in some cases it's already a mature technology. In some cases it's in development. Now here, this structuring works very well with femtosecond lasers. It works very well with green, typically 532 nanometer femtosecond laser, but these lasers tend to be very expensive and complicated, and so the question is whether it is doable also with an infrared laser, maybe pico or nanosecond laser. And here is an example what was done at the Center of Advanced Energy Research. Here once more the structure of the solar cell. Here we see the active area, which is working, which is actually collecting light and producing energy, and all this area here is the dead area. So now in this work, the group of a doctoral student, Peter Kubis, was doing a lot of optimization of the parameters of laser processing with infrared laser, and for this, at first you have to do some tests. The test cells consisted of a transparent electrode, which was so-called IMI, thin sandwich of ITO and metal and ITO again. Then top metal electrode, P-dot layer, and an active layer, the blend of P3HD, PCBM. And here, this table, I show this table because here you see how different is the optical and thermal penetration depth in these 4 materials under the 2 different lasers. So, as you see, the transparent electrode material does not absorb the laser light very well. Absorbance is a little bit higher at 520 and not higher at 1040. This is because the free electron absorption here. On the other hand, the thermal conductivity is not so good, and the thermal penetration depth is relatively low, and the efficient or general penetration depth is determined by these values here. In the case of silver, you have very small optical penetration depth of laser line, and much due to higher conductivity, much higher penetration depth, thermal penetration depth. In the P-dot and P3HD, it's also the way that the absorbance is very high. In P3HD, the absorbance of green light is much higher, of course, and that's why the penetration depth here is much shorter. So when optimizing the now the processing, you have to take account all these numbers, and you also have to do some screening. And here are a couple of examples where they use different pulse energies and different overlapping areas, and found the optimums at first for the P1 layer, which is the transparent electrode. The optimal values are somewhere in this region. This is just a magnified figure. And then doing the same for the P2, which is more complicated because if you do it with infrared light, then infrared light is not so strongly absorbed by the active layer. It penetrates the active layer and also damages the transparent electrode. And this is the problem. But what was interesting in this work that if you do it properly, so to say, then you damage this IMI in this region, the way that you have some higher regions at the edges, and they actually help to contact, well, when you're doing the P3 grooving, then you have to contact it to the bottom. And these edges, these higher edges of the IMI are actually helping to improve the contact. And here is the result. Visually, the result with an infrared sub-nanosecond laser does not look so good, but it works very well. This is the result made with a green femtosecond laser. It looks nice and smooth, but actually if you look at the electrical properties, there is practically no difference. So this is something that was, well, how you can do the optimization of laser parameters. Here another example of producing flexible organic or hybrid solar cells. This is an example where you make the active, transparent contacts and active layers on flexible PET foils and cover the top one with a conductive glue, so you can glue them together. In this, why do you need it? It's because making the metal contacts on the top of organic solar cells is not so easy. You can, in principle, you can print them using silver nanowires, other nanoparticles, but then you have a problem of which solvents you can use, which you can't use, and this way you avoid the problem of solvents. And now how do you do the structuring? You can do the structuring of these P1 and P2 grooves already in this lower part of the solar cell, and then you put on the top part with a transparent electrode containing silver nanowires here. And the trick was to do the structuring of the P3 line through the PET foil. This was done with a green laser which penetrates the PET foil. You can focus the laser slightly below this covering PET foil and just make a P3 groove into the top electrode. And this also worked very well. It worked well in organics and also in an example with a hybrid perovskite solar cell. Now, as a last example of how lasers are being used, not in solar cell production, but in development, you always have some defects in the solar cells, and you want to know what they are. You can characterize them electrically. Open circuit voltage, short circuit current, fill factor, but this is just an average value. You don't know anything about the defects. Now you can do some imaging, of course, like photocurrent mapping here. The left figure shows some silicon solar, actually a thin film silicon solar cell mapped by scanning a laser over the surface and measuring photocurrent. This is an example of a small area of an organic solar cell. And you can do further characterization by applying also simultaneously photoluminescence mapping. This is the emission spectrum. You can detect the luminescence intensity of the active layer in a spectral range, and do simultaneously current and PL mapping. Here you see the sample before, after aging. You see that the Actually, the active layer of the perovskite cell is very well working. It's nothing happened to it because the luminescence is homogeneous, but there is no current produced. So you know that an interface has been damaged. But now there are further imaging methods. This is an image or a slide from André Karl, who is actually doing actively this. You can use dark and illuminated lock-in thermography, so you see the shunts, you see which parts of the solar cell get hot. And you can also do, in addition, electroluminescence imaging and photoluminescence imaging. How many minutes? So this is just an example of good cell and a bad cell, where in electroluminescence on the left, or in the left figure, you see a very weak signal at some parts, and in the dark lock-in thermography, you see some hot spots and hot lines. So that actually this is the part which is shunted. But now, how do you know? You can position. Now you can see the defects. You have some lateral resolution. You know whether they are left or right, up, down, but you don't know in which layer they are. You have a clue. If you think what is going on, well, for instance, for photoluminescence, you don't need any contacts. So if there is something happened with photoluminescence, you know you have damaged the active material. If the active material is okay, but there is no electroluminescence, so you see that, okay, the injection of charges is not working well. But to have a better knowledge of this, there is some work going on with an femtosecond laser to produce the defects in a controllable way in different layers, and then do a full characterization of the solar cells, including all the above mentioned imaging methods. And this way you will have a very good description of defects, and later you can reverse this process, and just doing mapping you can tell in which layer you have defects. And now to do, it's not so easy to make these defects repeatably and controllably in different layers. So again, you have to start with determining the laser ablation threshold of different layers, which is done the way that you shoot a sample with single spots. You make holes, you measure the diameter of the holes, which is correlated the pulse fluence, and if you can rewrite this equation the way that you show the square diameter of the hole and the logarithm of the ratio of the fluence and threshold fluence, and then you can do a plot for different materials. Here is the logarithmic presentation of laser fluence, and here is the square of the diameter. And now at the point where the diameter is 0, meaning that logarithm here is 1, the fluence is equal to threshold, you can define the threshold values. And this has been done for the relevant materials in our test systems. And now you know that if you want to make a hole in a specific layer, you have to choose a value of fluence in the proper region. And this looks like this. In the electron transport layer, you can easily make a hole without damaging the ITO. Then you prepare the active layer, filling the hole, and just in the normal way, you cover it with the P dot and silver. And then you do a characterization and see what happens. What happens is that, I will skip a couple of slides, that if you make a hole in the electron transport layer, then you obviously don't see much electroluminescence, because there is no the charge injection is hindered. There is nothing happening in the photoluminescence, and in the dark lock-in thermography you see a less or a lower temperature, because there is no recombination happening. You can make the defects in the active layer. these defects have a much stronger effect on the electrical properties. Actually, I thought that I mounted or put the IV curves also in these figures, but for some reason they are missing now. So in the case of active layer, you have to be careful not to damage the electron transport layer below, so it's more critical. And what you see, obviously, is a hole in the photoluminescence and in electroluminescence. And if you do dark lock-in thermography, you see a hotspot in that you have a direct contact between electron and hole transport layers and a lot of heat dissipation. And now work is going on to apply this process to tandem cells where you have much more options to make the defects. One problem with this system is that if you are making if you try to make a hole in the hole transport layer on top of active layer, then the laser is much more strong. The whole transport layer is very thin, absorbs laser not so strongly, and the laser is absorbed by the active layer. So you are inevitably damaging the active layer as well. You have to find other methods to make defects to the whole transport layer. So this is an example how a laser structuring is used in the development of solar cells. So that's basically all. Thank you.
Questions? Yes, please.
My question is about the first part of your presentation. It's about those long holes that you put the metal inside them.
In silicon.
Yes. Mm-hmm. And I wonder if that kind of geometry can replace a transparent electrode.
I mean, it works well in silicon. And as I said, the coverage, you can strongly or practically eliminate the coverage of your surface with electrodes. So why not? A transparent electrode on silicon means an additional layer. Transparent electrodes. Which one would you prefer then?
You would like to have, you're talking about to have, two transparent electrodes? Because, from what I understood, it has this transparent electrode, he places on the top, the laser, and he comes with a laser from the top to do the process.
I think the question was about silicon and the holes, the through contacts.
Maybe this technology can help you replace transparent electrodes and
you mean
in other
use the same technology in thin film? I'm not sure, because for silicon there are chemical methods how to fill these groove or holes. I'm not sure how to do it with organic material.
Another question? Can I ask you something? Sure. Yeah, when you are doing the P1 and P2 and P3 lines, when you would like to connect the different cells for a module, you said that you're using one wavelength, so you have a femtosecond laser at green. You're using, just this wavelength in order to...
Actually, it would be preferable to have two wavelengths, green and infrared. Right. But this was the aim of one of these works that I showed, that it is much easier and cheaper to use in a production, only one infrared wavelength. And the longer pulse.
So and this means that you can do the job only with one wavelength. Yes. And the other thing that I would like to tell you, to ask you, is like, you have your electrode, you place your material, you are doing the P1, you place the other material, you are doing the P2, you are placing the top contact and you are doing the P3. Am I right? This is the process. I mean, there are other people that, they are placing all the layers and they are doing the process of when they have deposited all the layers. Is this possible in your laboratory? So they are not doing, in stages, but, they deposit the transparent electrode,
I mean, then you have
the whole transport layer, the active layer, the electron transport layer, and then the top electrode, and they are doing then, the lines.
But then you have to be able to get into the structure.
Yeah.
This was in one example with these laminated cells, where you really do, but it was only the last step. But this was focusing the laser into the structure, not on surface.
But even in this case, they build, they are organic solar cells like this. But they are not doing step by step, but they deposit all the layers, and then they are using the laser in order to formulate these lines.
I'm not sure.
I mean, it was like it is the lady in France that is doing this. I will find you the name. I will find you the name. It's like a Russian lady that's doing it.
By the way, concerning this
Actually, she's in Netherlands. I will find the name for you. Now I'm forgetting.
Concerning, once more, this laminated example, you could do the P3 also from the, before you do the lamination, you could cut the P3 and then put it together. But it would be very tricky to put it together exactly, because the P1, P2, P3 have to be close enough.
The P1 and P2 and P3 lines?
Tens of 10.
By the beam waste of your laser?
Yes, the beam waste in this case is now, in one of these examples, it was something like 20 microns, in another one 35, or it's this order of magnitude.
And this means that, if you are using green, the divergence will be higher, no? Compared to 1064. But you're using femtosecond in order to not induce thermal effects on the sides, no?
Yes, that's, yeah. Generally with femtosecond you get the clean cut.
Yeah. But you're using more pulses, I suspect.
More what?
More pulses than in the case of the nanosecond. Because you like
maybe yes, yeah. But I mean, it's different. If you're cutting into active layer, then green is much better absorbed again.
Yeah, exactly.
Than the infrared. Yes.
So any other questions? So I think that you're hungry and we should stop for our lunchtime. I would suggest to be back at 2:15, no? In an hour. All right? Let's say, thank you. Let's thank again Professor Osvet.